All right, in this video, I'm going to walk you through the process that you can use to sketch a polynomial of degree 4 that is written in factored form. And we're going to do that using the degree, the leading coefficient, the x-intercepts, the order of the x-intercepts, and the y-intercept. But before we get into that, be sure to sketch the graph of the like button down below so that other people can see this process as well. Now, the first thing we want to look for when drawing the sketch of a polynomial function in factored form is the degree. And the degree is actually really simple to pick out. All we really need to do is just count the number of times we have an x. If you look at this function, it appears that we have 3 x's multiplied. We have 1, we have 2, we have 3. But if you said that this was a degree 3 polynomial, you would be incorrect. And the reason for that is this pesky little exponent of 2 right here. Now that exponent of 2 tells us that we actually have x plus 1 times x plus 1. So we actually have 2 separate x's there that are being multiplied. So as it turns out, the degree of this polynomial is in fact 4. This is a quartic function, so degree 4. Okay, so that's the first key piece of information that we need to sketch the graph of this function. Now, if you've ever seen a degree 4 polynomial function, you know that they can take 2 possible forms, right? The first form looks generally something like this. Okay, I'm not using accuracy. It kind of looks like a W. The second form would be an upside down W or an M. Okay, so those are the 2 general shapes that a quartic function can take. But in this video, we're not going for general shape, we're going for accuracy. So in order to narrow down which one we're working with here, we need to take a look at the leading coefficient. Now the leading coefficient, or the LC, could be found by multiplying out the product of all of these binomials and finding the term with the highest power on x, which we know is going to be 4 because we're working with degree 4, and then picking out the coefficient of that term. But I don't actually care what the coefficient is in this case. I only care what the sign of the coefficient is. Now, because I'm working with a function that doesn't have a negative at the front, I know that the leading coefficient of this polynomial, when I expand and simplify, is going to be positive. Okay, so no negative, it must be a positive leading coefficient. So I'm going to say that the leading coefficient is positive. Now that's super helpful information because that tells me that we are not in fact working with this general form of a quartic function. We are in fact working with something that looks like this. So more specifically, we know that our quartic function is going to begin in quadrant 2 and end in quadrant 1. As I move to the left, my x values get bigger and bigger. My y values are getting bigger and bigger. And as I move to the right, my x values are getting bigger and bigger. My y values are getting bigger and bigger. So quadrant 2 to quadrant 1. That's sometimes referred to as the end behavior of the function. All right, so that's all we know at this point. We know that we're working with a degree 4 polynomial and our leading coefficient is positive, and our sketch is going to look something like that. And so what I've done is I've just erased that mess and replaced it with 2 arrows that indicate the end behavior of my polynomial function. Quadrant 2, quadrant 1. But let's start getting specific here and really start narrowing down what the actual function is going to look like. And to do that, I'm going to take a look at the x-intercepts. So the x-intercepts I can find by letting y equal to 0 and solving for whatever x value makes the function equal to 0. But since we're working with a factored form function here, the easiest way to do that is just ask yourself what value makes each of these sets of brackets equal to 0. And so as it turns out, the x-intercepts will just be the opposite sign of the second term in each set of brackets. Okay, so -2 for the first one, -1 for the first one, and 3 for the last one. So those are our x-intercepts. And I've just gone ahead and plotted those on our graph for us. You can already see that our graph is starting to take shape. We're not just working with 2 floating arrows anymore. But let's get even more specific and analyze the behavior of our function at these x-intercepts. And that's where this order term comes in. We use the term order to describe what is happening to the function at the x-intercepts. Now, in a lot of cases, we just see the function pass through the x-axis, but there are other cases where the function will behave differently. In order to identify the order, what we do is look at the exponent on each set of brackets that contains our x-intercepts. Okay, so for the first set of brackets, that x plus 2 is going to be an order 1 x-intercept. Since we have an exponent of 2 on our second set of brackets, that's going to be an order 2 x-intercept. And our last x-intercept of 3 will be an order 1 x-intercept as well, because we have a little exponent of 1 there. Now let's talk about what these orders mean. Okay, so an order 1 x-intercept means the function is going to pass through the x-axis at that intercept. So at -2, our function is just going to pass right through that x-intercept of -2. And the same is going to be the case at 3. We have an x-intercept of order 1 at 3, so our function passes through the x-axis at 3. But an order 2 x-intercept is different. When a function has an order 2 x-intercept, you're going to see the function sort of bounce off of the x-axis at the x-intercept. Okay, so that's the key difference between order 1 and order 2. Order 1 passes through, order 2 bounces off. There's also order 3, which looks like kind of like the function's just like sitting on the x-axis, but we're not going to get into that in this video. So a very loose sketch of what we're going to see here. We're going to pass through the x-axis, we're going to bounce back up and touch the x-axis, we're going to come back down, and we're going to pass through the x-axis again. But let's go even more specific and look for one more key piece of information, and that's our y-intercept, which we can of course find by letting x equal 0 and seeing what our y value is. And in this case, that's going to be -6. So I'm going to take a point and I'm going to drop it right there at -6. Now the last step here is just going to be going through and sort of connecting all of these fragments of our function to create the sketch of a polynomial. I know I'm going to start up in quadrant 2. I'm going to pass through that first x-intercept. I'm going to bounce off the second one. I have to come back down and pass through that y-intercept. And then at some point, I'm going to have to spin back around and pass through that final x-intercept. So as a loose sketch, it's going to look something like this. So I've cleaned things up just by removing all those preliminary sketches to create the graph of a quartic function with degree 4, positive leading coefficient, those x-intercepts, and that y-intercept. Now, of course, this isn't completely 100% accurate. We could, use the fact that this is a function and substitute some x values in, get some y values out, and really clean up the accuracy here. We can also use calculus and derivatives to plot the local maximum minimum, but that is beyond the scope of this video. So here you have a passably accurate sketch of a degree 4 polynomial written out in factored form. For more on polynomial functions, you're going to want to head over to this video right here next, and I will see you there.